All right, let's dive in. Today we're going on a quest for what you might call true AI. And it's a journey that could take us way beyond the simple ones and zeros that have powered our world for the last 100 years.
You've felt this, right? You ask an AI to write a poem, and what you get back is, well, it's technically a poem, but it's missing that spark, that soul. It can calculate at lightning speed, but can it actually understand? It seems like there's something missing, and that's the big question that's pushing the entire field forward.
And here's the gap, laid out plain and simple. On one side, you've got the AI we have right now. It's all about logic, pure calculation, and because of that, it's pretty predictable. But the goal, the real target, is artificial general intelligence, or AGI. And that's a whole different ballgame. We're talking about intuition, genuine creativity, and ideas that emerge in ways we can't predict. So what's the barrier? What's holding us back from making that leap?
Well, a lot of the most interesting new research suggests the problem is baked into the very foundation of modern computing. It's the binary system itself. It seems we've run smack into what you could call the binary wall.
Think about it. Our minds just don't operate in simple on or off states, do they? Human thought is a spectrum. It's messy, it's continuous, it's full of maybes and what-ifs. And the rigid logic of binary just isn't built to handle that beautiful, chaotic complexity.
So, if on and off is the problem, what's the solution? We have to start thinking beyond that switch. We have to step into the wild and wonderful world of nonlinear systems.
And the analogy here is just perfect. A linear system is like a basic light switch. You flip it on, the light comes on. One input, one predictable output. Simple. But a nonlinear system, that's the dimmer switch. You slide it just a little and you get a whole range of brightness. The relationship is complex. It allows for feedback, for surprise, for things to get interesting.
This is literally how nature builds complexity from the ground up. You start with something simple, it enters a system full of these rich feedback loops, and what comes out the other side is something incredibly complex and often totally unexpected. I mean, this is how we get everything from weather patterns to the intricate swirls on a seashell. That is nonlinearity in action.
And this isn't just some abstract idea. There are brilliant researchers out there right now trying to build this kind of thinking into AI. We're going to look at two of them who are working on the same goal, but from completely different and totally fascinating directions.
First up is Mitchell D. McFittridge. His idea is, well, it's pretty mind-bending. He's working on something he calls quantum retrocausality. What does that mean? Basically, he wants to build an AI that can use its own future outcomes to adjust what it's doing in the present. It's almost like giving the AI hindsight, but in advance. It just completely turns our whole idea of cause and effect on its head.
Then you've got Clenio Araujo Padilla. He's looking directly to the natural world, specifically to the physics of how waves work. His big idea is to create an AI that doesn't think in rigid steps, but in continuous, overlapping waves, just like waves in an ocean, to better capture the fluid way our own minds work.
So let's put these two approaches side by side. You can see McFittridge is really focused on the software, on the flow of time within the algorithm itself. Padilla, on the other hand, is looking at the fundamental physics, and he's thinking about both the theory and the actual hardware. So one is trying to rewrite the rules of time for software, while the other is trying to build a new kind of physical brain from scratch.
Let's go a little deeper on Padilla's vision for a minute, because this leads to a truly revolutionary concept of what a computer could even be.
At the core of his research is a complex wave function. Now, don't worry, we're going to skip the heavy math, but here's the gist of what it does. It's designed to act like a natural, flowing wave. It can hold multiple possibilities at once. That's a concept called superposition. And crucially, it has that nonlinear secret sauce baked right in. And the result? It spontaneously generates these incredibly intricate repeating patterns called fractals, which just so happen to be the geometric language of complexity we see all over nature.
And here is where it gets absolutely wild. This isn't just about a clever piece of code. Padilla's work is a blueprint for an entirely new kind of computer, one that would use the nonlinear properties of light passing through crystals to actually perform these calculations physically. It would be, in essence, a computer that literally thinks with light.
Now, these researchers aren't working in a bubble. The ideas from McFittridge and Padilla are part of a much bigger, much broader scientific movement, a quest to build machines that think in a fundamentally different way.
You know, this is all part of a larger story. From building brain-like neuromorphic chips, to harnessing the weirdness of quantum computing, to processing information with light, scientists all over the world are looking to nature for a new blueprint. It's a huge shift, a recognition that the binary road we've been on for so long, as incredible as it's been, might not be the one that leads to true general artificial intelligence.
Which really leaves us with one final, awe-inspiring question. For a century, our computers have spoken a language of absolutes, yes or no, 1 or 0. But if we can actually pull this off, if we can build machines that think in waves, in feedback loops, in infinite shades of gray, what new ideas, what new forms of creativity, what will they even dream of?